Good morning, good afternoon, or good evening, wherever you are in the world. Welcome. My name is Zaim, and on behalf of the entire Total Materia team, I would like to thank you for joining us for the third session of Advanced Finite Element webinar series. Our goal is in this series is to go beyond theory and explore how correct material property selection can dramatically improve the accuracy of simulation results, reduce repetitions, and ultimately support innovation with confidence. On the stage, Mr. Erdido and Bartu here with us today. Please, Erdi.
So, we had been 3 webinars for now. This is the last one. So we are really deep down to do the advanced topics in this one. So basically, I want to begin with introduce myself. So I'm Erdido, and more than 12 years experience on finite element analysis. I have expert level Abacus knowledge, and also the other solvers like Nasran, Elastine, Radios, or Abstract, etc. And the system and component level CS simulations I've been working on previously, and of course dynamic and thermal behavior of materials. And on the other hand, the fully integrated optimization loops with the Python scripts and the 3 years of mentoring and 5 years of project management experience I have. So, Bartu, go on, please.
So, hello everyone. I'm Bartu Süleymanoğlu. I'm junior structural analysis engineer. So I have knowledge in Abacus implicit, explicit, and Elastina. My main focus on composite materials and structures, design and analysis of metamaterials, and I have knowledge of machine learning and deep learning for engineering. Basically, most of them for metamaterial design, inverse design. So okay. Thank you. Yeah.
Thank you.
So here is the agenda. That's first we go through the deep learning for results of strength analysis with Bartu, and also the next one is topology optimization and the fatigue investigation approach of related materials with myself, and the last one is the impact analysis example in Elastine. So also Bartu will provide this one. So, and okay. Your turn, Bartu.
So, okay, first we need to define the machine learning, deep learning, and AI. So it is these terms. Sometimes it's fuzzy. Sometimes people use these terms a little bit different, I would say. So, but we can say that AI is the broadest umbrella. You can think AI as any technique that enables computers to mimic human thought or process. So machine learning is a subset of the, AI. So machine learning systems discover statistical patterns in data between inputs and outputs, and generalize these patterns between unseen inputs, I would say. So for deep learning is the, I would say, automated system. It's a subset of machine learning as well. It can abstract really complex relationships, and the difference between machine learning and deep learning is machine learning sometimes needs human intervention, and it is only, I would say not only, but it is good on low data, but deep learning has, you excel in really big data. Okay, we can go on.
Yeah, so this is very interesting topic. Sorry to interrupt, but predictor, which we created 2 years ago, and it's been like 3 years in behind. We have total 5 years of work for this. Now I understood better deep learning and machine learning, and deep learning basically needs data with where Total Materia have 600,000 of materials, 25 millions of records. So
Yeah,
that's
you need
how
that.
it's learning, right?
Yeah.
So
It's
actually, that's
you
what I'm
need
saying.
that
That
data. Yeah, to get a really
Amazing,
result in deep learning.
you have
amazing.
a big data, so you can predict much more accurate. Am
Yeah,
I right?
AI,
Yeah. You
AI
need
gets
that.
better,
Yeah.
right? Like every single every next month it gets better and better, just like it's learning basically, and it's quite interesting topic.
Yeah. Okay.
That's one.
So
Yeah.
I think okay. So where this concept came from? Basically, it came from the biological neuron. So because we're just trying to mimic the human, the process of human thought, right? So we need to model this in the computer. So as you can see, we can when we model this neural networks, it's called multilayer perceptron. As you can see, so we can go on. I will go into detail in the next slides. So as you can see, what we are doing is we are just creating, or we are just trying to understand a relationship between input and output. So it is we can clearly say that it is a universal approximation algorithm, because you can use for different things with using pretty much same neural network structure, I would say. But in explicit programming, like normal programming, I would say, you cannot do that. You need to customize your program in order to get a meaningful result, or in order to not get an error. So it is a really important thing. And by the way, as you can see, these equations are just a linear combination between them. You're just making a regression from this, but we're giving some nonlinear activation functions so that we can model really nonlinear concepts and relationships. Yeah, we can go on.
Basically, what I understand that, so we just mimicking some outputs and creating relationship between the input and output. Am I right?
Yeah.
So according
Yes.
to this,
Yeah. With a given data set. Yes. Yeah.
yeah.
So this is how the forward pass, or when it is not a whole training concept, by the way, just forward pass. So you're just getting input and output. So as you can see, here you have an expected value and an input layer. So you're just trying to get an accurate result from it. But by the way, from the start, as you can see, it is not really accurate because it's only one feed forward process. And I need to say that the weights, as you can see, in the start, it is arbitrary. Sorry, so it is randomized. So by the way, that means if you have a neural network, you can get different results as well, because the initiation of this arbitrary weights, because it affects as well. It happens, but in really good neural networks, yeah, you don't get it, or it's not a much big difference, I would say. Okay, we can go on.
Actually, so can we say that it is a similar between the genetic algorithm with the deep learning algorithm? Can we say it, or are there any differences?
It's just genetic algorithm is it's a explicit program. So it's just like a normal programming. So it tries to find the optimum solution, and sometimes it creates a new new data, I would say. But for this, you are not creating new data. You can maybe compare the genetic algorithm with generative AI, but also they are not same, because in generic algorithm it is explicitly programmed, and you have a really, I would say, strict rules for
Yeah,
this.
there will be no training at the end at the generic algorithm. I
Yeah,
understand.
yeah. You're just trying to find, it is a heuristic, so you're just trying to find the optimum solution. Yeah.
They have rules. Yeah, exactly.
Okay. So we can go on.
Okay.
So the important thing is, and I would say the most important thing, because after these concepts are given to the world, it changed the neural networks, machine learning, deep learning. So the thing is, okay, we have expected outputs and calculated outputs for, you know, first feed forward process. So we get that they're not similar. So what we need to do is we need to, you know, accurately calculate this, right? So we need to go for this expected values. So in order to do that, we can say, okay, I can define a loss function, which means that it is the difference between, by the way, loss functions can be different. For this is a just an example, and it is, you are selecting your loss function in your need. So you cannot use every loss function for every you know, type of analysis or type of algorithms. So when we get this loss function, okay, we can say that we have a total error in the neural network. So how can we decrease it? So we can say that if we can take a gradient of this, so we want to minimize this loss function. That's the whole thing, by the way, and it's called backpropagation. So the backpropagation is an algorithm to compute the gradient of the loss function with respect to each weight. So, and after that, in the neural network propagates this error back from output layer to input layer. So you know that you know your losses, you know your gradients, and after that, from this, you can update your weights. And when you update your weights, you will get accurate results because you're just trying to minimize the whole thing. Go for it, please.
Basically, you are doing a gradient algorithm to reach the local optimum. Exactly.
Yeah,
so
local minimum or global minimum, but global minimum is complicated.
This is just for the loss function, actually, not the global optimum value, what I understand. So this is just only finding the loss function, actually.
No,
yeah,
it is like it, but it's just what you're doing is basically you're just trying to find how this each weight in the neural network contribute to the error. That's the thing. So and after that, you're coming backwards and updating the weights according to it, and again you're forward passing and getting another loss function or lost value from it. That's the thing, basically. So we can go on.
okay.
Okay, this is the gradient chain rule for the backpropagation. As you can see, the every weight contributes to the output. So you can use chain rule to calculate the gradients. We can go on. Okay, so and after that, as I said, you can update all the weights and run this sequentially. So at the end of the day, you will get a maybe pretty good neural network, I would say. Yeah, please go on. So we said that we are optimizing the weights. So in deep learning, we have, or machine learning, we have different types of optimizers. As you can see at the left side, it is used for different, not every optimizer is suitable for every type of a problem. So you need to use different kind of optimizers. And also you can just use this to find how our performance, how the optimizer performance or optimizer type affects the performance. And the other thing is the learning rate. So when we are doing a gradient descent, we need to find a step size or a learning rate, so that we can, I would say, get closer to the local minimum or global minimum without, I would say, without any it's just a
It's just a gradient algorithm we are approaching in here.
Yeah, it is.
So it depends on what is the learning rate which can be handled. So if we took the too small, the iteration will be longer. If it is the too large, we cannot find the optimum area because of the too large weights.
Yeah. That's all.
Yeah.
Yeah, you're right. Okay. So how can we use this we use these algorithms to inverse design of metamaterials? So the concept behind the metamaterial design is really complicated thing, because you don't have a good way to, I would say, design these materials. You don't know, or you don't have a behavior or a pattern for these materials. So classical design algorithms could be really painful, because you don't know, you're just trying and getting FEM results, and after that you're just trying to get a closer stress strain curve to your model or your needs. So what we can do is, in this type of machine learning algorithm, so we can say that we are starting with the inverse prediction module. So we have an arbitrary stress strain curve, and from the stress strain curve, we can say that we can put this inputs into the inverse prediction module, and from that we can get a design parameters of metamaterial. So it gives us okay, this geometry can be quite useful for your metamaterial, or it can be suitable. So from that, after that, we can take this design parameters and our curves, and put it to the curve type classifier. So what curve type classifier does, it tells us the behavior of the of our straight strain curve. So, and from that, we are getting a type of a loading type or response type, like linear response, plastic yielding, buckling response, multiple whale peak and valley response. So after that, if when we put all of this information to our curve feature regressor, we can get an optimized or a suitable design candidate for given arbitrary stress strain input. So this is a really, I would say, a little bit basic, because it is not for this work, it is not a generative algorithm. So in order to get a really big data set, you need to sample it pretty hard, by the way. So or you need to just scan all the design space. But in the generative AI, the generative AI can create its own samples. But for this, it is not possible, because it's just like acts like a library, I would say, pretty fast library. So we can go on.
Basically, at the end, we are just giving the parameters that could be changed. But firstly, we need to train the algorithm. So we have some parameters, different types of geometries maybe. So for example, we have a compression analysis. So we know the responses, which is maybe a linear response, or as you can say, maybe a buckling response or different response. So the algorithm just train itself that which parameters or which geometries could fit these responses.
Yes.
Then we are giving to the algorithm which one could be suitable in our final stress strain diagram. So it predicts which geometry, I mean, which parameters should I give in and should I take into account. So then the question is, at the end, should I get the one last result, or the bunch of probabilistic results?
Yeah, the thing is, in the metamaterials world, different types of geometries can have a really similar stress strain curve under the compression. So I think the best way to compare is to get multiple results, which is done in here, so that you can look what is happening not in the stress strain curve, but in the maybe you can understand the local collapse mechanisms, localized stress values. So it must be done. Otherwise, I think your design process would be quite poor, and sometimes maybe you cannot get what you want from it. Yeah. So it must be, again, iterated as well.
I see.
Okay. So as you can see, this is the results from this work. It calculates or it gives the design curves, and from that you get the results, these kind of geometries. And you can understand that it's really pretty understandable, these kind of I would say behaviors. Maybe I can say that for the fifth, you can understand that, okay, we will have a local collapse. Yeah, in the compression you will see a local collapse, and you're seeing it. You're seeing a relaxation, like a relaxation effect or a local collapse effect, and after that densification. It is pretty understandable, and it gives a pretty accurate results, by the way.
So there is also another that normalized root mean square error prediction value is in here. So we have a target curve and the measured one is what we have the end of the simulations. So we are predicting which parameters, which geometry fit, or what we need actually.
Yeah.
So as you said before, you just said that the mimic of the human behavior, the general AI solutions. So as a human, actually, I would like to search which geometries, which parameters need to be handled. So there's lots of works with this technique. So you may just dismiss the human behavior instead of you're just replacing with the deep learning algorithm to select the final geometry or final parameters you decide.
I think it is really important because I think the best part is, for this work, you can really easily iterate between these kind of geometries. And the other thing is, an inexperienced engineer could use this deep learning algorithm to design the structures with metamaterials. I think it's a really, really good thing, by the way. Yeah, you're just dismissing the human factors, but at sometimes in the design process, it becomes much more faster, I think. I don't know what you think, but
yeah, Sure, but and the first of the whole algorithm also needs a human that define which parameters, which geometries should be applied on this algorithm. Actually.
Of course, only the expected or need the only thing you need is a stress strain curve, and after that the algorithm does everything. That's the I think that's the beauty.
Okay, thank you, Bartu.
Yeah,
so
thank you.
I'm jumping to the optimization solutions. In the agenda, the second bullet, the second topic is a topological optimization. But first, we need to understand the differences between the parametric optimization and the non-parametric optimization. So parametric optimization was also mentioned about it. Some parameters need to be handled. As you can see, some features, some radiuses, some dimensions in here, the changing by the inputs, and also we have some results and some feasibility at the end. These are the curves could be fit, and these are the parameters can be handled, and this is the final and optimal results. This is a parametric optimization approach. So many techniques we can mention about it, but this is not the today's topic actually. But at the end, so you have some response surfaces according to the input parameters. So you can define everything, every parameter and every parameter behaviors affected to the results. In non-parametric optimization, I would like to say, so for different optimization we can say about it, we can mention about it. One of is topologic optimizations, and today's topic is also about it. And the other one is shape. I will also mention about shape later, bead and sizing. This one is really interesting that, for example, in your finite element model, you have some bunch of shell elements, and changing by only thicknesses that you are searching for some eigenvalues or some bending stiffness, for example. So we can go for it. In the bead optimization, you have some design areas that could be changing the height of this feature. You are not changing the thickness, you are just changing the feature dimension, the feature height dimension. So another one is the shape optimization. Shape optimization means that we have a finite element model with nodes and the elements related to each other. So by changing on the surface, and this means that changing the nodes, the surface nodes, inner or outer of the surface, to changing the geometry actually. So this is useful for fatigue analysis, by the way. So I will also mention about it. And the topological optimization is it's a really different approach that's just think about you have some like the density factor. So which element should remove or add? Actually, there will be no adding in topology optimization. There will be only removing. But the program, the algorithm says that this element should be fulfilled, and which means the density equals to 1, or this element could be fully removed. It also equals to 0. But what if we have a 0.6, 0.3? So these are the colors. As you can see, the right one is density is equals to 1, and you cannot see right now because it's hidden. If we show the whole elements, you can see the color is blue, which means the 0, and the whole color is normalized between the 0 to 1 actually. So in topological design variables, so we mentioned about that some parametric and non-parametric approach. In the CAD model, we have some parametric dimensions. For example, a discrete or continuous differences or some material properties like Young modulus Poisson ratio, for example. These are the parametric approach. In the non-parametric approach, you have no parametric actually. So you are searching for the final solution. Okay. So the targets, it's the similar between the parametric optimization approach. You have also a minimum, local minimum, and the local maximum, and also feasibility area. So you're just maximize something or minimize something. For example, you may want to minimize the stresses and also maximize the overall stiffnesses, or you could be able to minimize the mass, etc. actually. So in order to do this, you will have some restrictions and constraints. So we will also mention about some symmetry conditions and the casting conditions. Please don't think about it. This is the only way to manufacture it or only way to get the parts by additive manufacturing. This is the really big whole lie actually. With the restrictions, for example, the casting restrictions, you may able to create your part as a cast part or forging part. You may also able to create your part as a machining or NC part. So you need to think about the what is the restriction, what is the constraints for your manufacturing effects. So these are some symmetric conditions. As you can see, there is a plate in here, some the boundary conditions applied in here, and there is a force in here. So without symmetry, we can say that this should be the end of the geometry with the topological approach. So if you have a plane symmetry like that, as you can see, there is a plane symmetry, and the point symmetry, and rotational symmetry, for example. These are some symmetrical conditions approach. So you may think about which could be implement on this design. So casting restriction, what I'm saying that this is the two component that which is the actual part and the mold, and we have a pull direction. As you can see, through the pull direction, we have a surface that need to be have little bit differences from the parallel surfaces. So if you have this feature, you cannot pull the directly from the component. This could be a restriction. So another example that, for example, you have the molding direction in this one, this direction. So without restriction, you have a really bunch of some thick elements in here, thick parts in here. So with the molding direction, you have just only one part like this one, actually. So design responses in topological optimizations. What it means that design responses means responses. So it could be related with design, for example, the combination of load cases, some weights or some inertias, the results, maybe the stiffness and the displacements. In the finite element analysis, these are the responses at the end of the your results actually. So there is also another topic that I need to mention about it, the load case scenarios. So we have a bunch of load cases like this one. So there is a restriction here, the bottom of the surface. So load case one, applying this force in here, here, and the third one is here. So all these results is the different solutions, so different geometries. So the goal is reduce the total volume to the 70% actually. So if we have a combination of these load cases, for example, we have 3 loads, but it will not affect the same time. It will have some weight factor. Bartu also mentioned about the weight factors in deep learning. So the weight could be different according to your scenarios. For example, you have a really really low probabilistic scenario that you may also constrain the different weights of simulation object. So you need to constrain about it, but mostly the general engineering approach that we have just weighted the same amount of the whole load cases actually, generally, by the way. So the strategy is in the topological optimization that need to be some questions need to be asked actually. So we have a model and the design variables. Choosing the design variables, which design variables we are talking about. The variables means the which elements or which area we are talking about, and the finite element analysis responses. Actually, this is another challenge that if you have the whole model, for example, 2 or 3 middle element, and you just want to go for the topological optimization. So this is actually not happen these days, because even if you have a really good CPU hardware, but the time will also need to be considered. I will also mention about the control-based and sensitivity-based algorithms, but it will be different. I will also mention about it. And the objective, what we are looking for. We are looking for stress, minimizing the stress, or we are looking for the contact pressure, or we are looking for the reducing the mass. So choosing the constraints also. As also mentioned about before, the symmetric constraint and some how can I say the mass reduction constraints, for example, and the design variables. Number of different design variables could be tough, because if you have a really larger number of design variables, it could be hard to find the final solution. So this is the controller-based and the sensitivity-based optimization differences. In controller-based optimizations, that's a very simple task. For example, you have a part that needs to be weight reduction. So you have a stiffness. Basically, just the one surface have a boundary condition. The other point or surface have some loads. So your restriction is reducing the mass, for example, 60% of the total design variable elements. So basically, this is a controller-based optimization. This is more like the gradient-based algorithm, which Bart also mentioned about before. This happens to really fast solutions, and you just wondering what will be happen if there is a restriction, there is a one force in here. So in this sensitivity-based optimization, you can also affect, and you can also change the eigenfrequencies, not only the stiffness, but also other things. For example, the fatigue level. I mean the cycle of the total life of the parts actually, or I mean the contact pressure or some stress gradients you may also define in sensitivity-based optimizations. So it will be much more complex algorithm. You can also define the multiple objectives and several constraints in sensitivity-based optimization. So you don't need to just directly apply one load scenarios. You can add the different load scenarios, or you don't need to go for the only static solution. You may also go for the steady state, the heat transfer, or maybe the coupled thermal structure analysis. You can go for it basically. So we also mentioned about that. This is actually need to be important, the number of optimization iteration. In controller-based algorithm, generally uses the maximum iteration number is 15, but for the sensitive-based optimization, we cannot predict. So basically, it's 30 to the 45 number of the iterations could be normal for the general sense-based optimization, but this number can be higher. So it could be a more than 100 iteration. That means that would be the over 100 simulation could be run. So as you can see, this is differences. We also told about it. There's a restriction in here, in boundary condition, in here and here. We have a load in here to downside. The left side is the controller-based algorithm, and the right side is the sensitive-based algorithm. As you can see, controller-based algorithm, it's nearly the whole elements, if the whole elements nearly 0 or the 1. In the sensitive-based algorithm, as you can see, some elements, it's between 0 to 1. So it will be decided to the user. It should be a surface like this one, or it could be changed. And they rerun the analysis with a different mesh approach. So, okay, final slide for my topology optimization. It could be final, yeah. So in the optimization strategy, if we begin with the finite element model of design space, we need to ensure about which areas could be add materials for the design space. This is the design space. So some areas could be frozen, like this area. So this area could be frozen, and these are the design space. And then I go for the topological optimization in here, and then smoothing and generation of validation. This means that the cat generation, actually, we have at the end of the topology optimization, you have a like STL file or some IGS file, but this need to be handled with the CAD program like CATIA or SolidWorks or NX, whatever you want to work about it. So at the end, you have a fully CAD platformance finite element model, and then you will rerun your model and get the validation run if it is okay or not. If it is not, so for the local stress areas, you may go for the shape optimization, which I've been shown before. So you may smooth these areas with the shaped optimization, and the final, you will get the optimized CAD reconstruction. So at the end of the shape optimization, you will also have a broken CAD file, which means that the STL or RGS file. So you cannot directly use your geometry at the end of shape optimization. You can use your finite element model, but you cannot use direct the CAD at the end of the shape optimization. This is the optimization area. So if you go for the fatigue, basically I can say that the two different approach in the fatigue algorithms, which is the stress-based fatigue and the strain-based fatigues. These are the general approach, actually. If you go for the high cycle fatigues, that you may use the stress-based fatigue algorithms, stress-based fatigue approach. If you have a low cycle, you need to prefer with the strain-based fatigue, but also applicable with the high cycle fatigue, actually. So why is fatigue loading important? So basically, you have not very smooth, very basic load application in real life. In real life, your measured load data like this one. And if you separate with the different direction, you have like this one. So it's for example a multiple road events you may consider about it. So you need to be clear your data, and you need to understand your data. So if it is applicable or not, or is there any error or any repeatable events in this data, you need to focus it. And oops. And another thing that's, if you're considering the 3 types of loading like this one, so we have a parts and the test bench in here. So we have a different 3 types of loading. One is the little bit lower, and the other one is the higher amplitude, and the third one is the combination of first and the second one. So at the end, first and the second one have the broken area is the same, but the combination of these 2 loads could be different. So loading data is really important. You need to focus on if there is any overloading on your fatigue load. So it depends on the historical approach. But we are saying that if it is a high cycle fatigue, we assume that this is a linear approach. So we can just sum the whole damage, and we can just search the fatigue results with the linear approach. And this approach will not depend on the historical events like overloading. So you need to change your approach actually. So there's some different techniques like the rainfall counting in here. So defining your which cycles could be similar to the basic loading scenarios. So with this technique, you may go for these load events under the repeatable number of repeatable events in here. So basically, you can use your minus rule, the life cycle fatigue approach. One last thing before we go for the total materia. So the surface finish also affect the fatigue values, the fatigue results. You know, there is a KT factor that affects on the which is the affected by some geometrical events, some surface finishes, or anything else actually. So you need to also considering about this approach actually. Okay. Zaim, are you there?
Yes, sure. I was following your design. There are some cracks on the design. Maybe would be the best to start with CAD design to define material, or in Total Materia there is an option that you can uh, basically check the materials different properties, right? So you will be able to find maybe more durable material, because that just reminds me from earlier in my career in Total Materia, 6 years ago, I guess, when Toyota engineers, they were looking for one specific material from their, historical use, and they wouldn't be able to find the material, and we actually find that replaced standard new up-to-date material information, and they were not sure if this is the correct material or this is the accurate material to use. But this new material, basically it was the steering wheel column, all right? So they added new ingredients, yeah, content inside the material. That's how they updated as silicon metal. Silicon metal content was higher a little, because that gives that material to flex more before it breaks. So, and one of my first technical support help was in Total Materia, and I said, all right, so this is the deal. This is very, very much related to materials, I mean, behaviors,
I
right?
I want to ask a favor. Is it possible to show us the how can we find? Actually, I need a chart that there is a
Mhm,
density or Young modulus that which material can be fit. This is really important um, when we are
mhm,
working on some topological optimizations or some,
mhm.
and also Bartu mentioned about the parameters. So I need some minimum and maximum areas can be fit. We may
Uh-huh.
also match with the price values also. Not only the density and the Young modulus, we may also have a price limitations. Is there
Well,
possible in Total Materia that we can just figure out the which areas should be seek for optimization or the fatigue level maybe? Can
well,
you share your
yeah,
feedback? Yeah.
yeah. This is not only related to material mechanical physical properties, right? In each individual, my presentation and uh, whenever I introduce tool material or in my webinars, I'm always mentioning that there are a lot of things that you need to take into account, right? So here's an example. I believe you can see my screen, right, in Total
Yeah.
Material platform. So
Yes.
this is my favorite material list, basically, in different classification, different types of material. This could be a right candidate for my design, and I'm looking for like some okay, yield strength, tensile strength value in the same time. I'm checking if they have a stress strain fatigue data in the same time. I'm just checking this material if they are suitable for my design. But still, this is not enough in most of the cases, right? So I want to add them to my material list builder to check. Actually, I need to compare this material, right? And somehow I can compare up to 100 materials side by side, but it's more effective way to move this material list to analytics screen. Well, this is what I do. It's very easy to compare all these materials. Okay, these are suitable for my design. I want the lightest one, and definitely I need the cheapest one in the same time because titanium will be very light usually. But well, these are the price range. Oops, we have some very expensive material right here, but at the same time, density level is not that good, right? We have very cheap material, but very high density, so it is very hard. Uh, so I need to focus on this material list here. This is how I can see all these materials side by side. Still,
So
I have
basically, I
cheaper
can
options.
understand that.
The
So I
lightest.
have the limitation. I can see that
Hmm.
1.2 to 1.9, as
Yeah,
I can see, is a density
yeah.
limitation according to the price. Can we also recreate this chart? Not individual, not the price. I want to add the Young modulus, for example, modulus of
Mhm,
elasticity versus density. It could be much more better to if you are
mhm.
working on the eigenvalues or looking for the MVH analysis. Actually,
Definitely. I'm checking all these materials again, and I'm adding not material but the property comparison. Now I can add like same density, same maybe pricing, but in the same time, what did you say?
the modulus of elasticity,
Models of elasticity,
yes,
and what
this
else
one.
we can add like yield
Oh,
strength at the same time,
yield
right?
strength, yeah, could be good actually.
Hmm?
Could be very good actually.
And tensile, still we have like up to 5 different properties in the same time. So these are the materials, but well, I want to see actually all of them together. What about a radar chart?
Cool.
So
That's good.
some
That's good actually.
some of
Yeah.
these material have you know different high side models of elasticity. These are very high tensile strength, and some of them are very low. as I can see, if I want highest tensile strength value here, you know, like I can check all these materials in one chart. So in the same time, as you can see, all this data set here, right? So this is the radar chart. I can compare the properties. I can compare some materials diagram individually, you know,
And
all
also
of
we
them
can
together.
save these materials, right?
Well, this is saved material list,
All right.
definitely, and I will be able to share with my simulation department, let's say. Still the same. I'm just clicking any properties that I want to see here, including coatings, joints, and suppliers, if I will be able to purchase this material, right? So these are very, very important properties that I want. I have 100 materials in my list, and I want to see the highest density. You see, density range I have. Like I want to see highest tensile strength value that I want to see, and this material is good. And yield strength, still see the difference in between yield strength and different heat treatment, different forms of the material is giving you different, definitely different values. So you need to understand material behavior, but not only the material and the number of the material and general information about material, but let's go deep into this material card. What makes it difference 205 to 1229 megapascal difference? Like you see, it starts tensile strength 485 to 2450.
On
Huge
which
difference.
condition? Actually,
Yeah,
it
these are
depends on which condition
this
we
is
are
the
looking for.
same material, but look at this, how many different heat treated
Yep.
form we have. Like, see, we have bars, castings, as you mentioned earlier, fittings, and all these different forms, including different dimensions. Like we have 2 millimeter sheet metal and 8 millimeter sheet metal. It's gonna be totally different story, right? So it's not only about the material, but deep into this material properties, you need to understand not only what material we are talking about, but what actually details we are talking about. Temperature dependent values, right? The mold processes. I have one of our users technical question that they are using CATIA and they are designing the mold. Everything is fine. First 50, 60, 100, 150 part is perfectly working. And after that, mold is getting warmer. And it goes up to 80, 90 degree, 120 degree. It gets warm, and then mold shape is changing so that you are not getting the same results. So he said, okay, I am the mold designer, but something is wrong here. And we find out that the mold is changing its shape when it gets warm.
That's why
So
we are doing our jobs, actually.
yeah, definitely. And
Yeah.
he needs a lot of details, right? He needs a lot of data about the materials to understand why this mold is changing its shape, why this material is not suitable for this design. We have heat
Sorry for
treatment
interruptions,
options.
but
Yeah, please
we
go on.
don't have much time for now. But we have also an Einstein example in who Bartu also will be mentioned about it. Can we go back to the presentation if it is okay for you?
Sure, sure. We have LS Dyno options too. All I want to mention in this way, and please go on because there are a lot of things to talk about the material and just uh, Bartu, would you like to share your screen?
I can share my
Uh,
screen. If
yeah,
it
All
is
right.
okay for you, you can make me presenter as well.
Yeah, sure. I will choose you as a presenter to continue this presentation. Thank you.
No, you're welcome.
okay. So,
Sorry. Yeah, this one.
okay.
Okay, go on, Bart.
Yeah. Can you hear me now? Yeah. Okay. So back then we've done some impact analysis in LS-DYNA about crashworthiness of a composite tube, which is a CFRP tube, by the way, carbon fiber reinforced plastic. So there's some modeling techniques we needed because in LS-DYNA we didn't have a continuum shell model like Abacus. So as you can see, there's a chamfer in the geometry. This is because if you don't have a chamfer, you will not have a kind of delamination you want to see in this analysis. So what we have done is we just created an idealized section for it, as you can see in the middle section. Otherwise, our system will buckle. So we will not get pretty good results for in terms of crash.
At the end we need a trigger mechanism.
Yeah, like it's a trigger mechanism for crashworthiness, applications. Okay, we can go on, I think.
Sorry.
So this is our mesh body, and this is our boundary conditions. We used rigid wall impactor for it. It is 108 kilograms. We can go on, I think.
Okay. So basically we have two parts.
Yeah.
Which both are composites modeled in here. Okay.
Yeah. And we used enhanced composite damage material 54, 55. And these are the material properties for one CFRP lamina. So we just modeled in the LS-DYNA as a layup. Okay.
But we have different actually the stack direction.
Yeah, of course.
Here. Yeah.
Of course. Yeah. It is. Yeah. We can go on, I think.
Yeah. Sure.
So the contact properties is really important. So between those two different composite tubes, we used a contact automatic one-way surface-to-surface tie-break algorithm. And for the general contact between surfaces, for composites, all the I would say the rigid impactor, we used automatic single surface contact. And by the way, for this analysis, we didn't use any cohesive zone because it's a preliminary analysis, I would say. But you can implement it in this contact definition in one-way surface-to-surface tie-break. You can use cohesive zone method.
Type options actually.
Yeah. We used, I think, the two. You can define it with 9, option 9. Okay, we can go on. So we can see the results. Okay, as you can see, we have a different type of failure mode. So what we can say that, as you can see at the start, it is 45 minus 45. They're pretty much same at the start. So in the outer layers, it's same. But in the inner layers, it differentiates. So what happens is, by the way, the left side has a higher impact absorption. This is because the direction of the impact is with the direction of the fibers in the 0 and 9. I would say 0 at 0 direction. So because of that, you have higher stability in your system as well. Because when you look for the left side, right side, you have an imminent cracking and collapsing in the structure. But in the left side, you have a more progressive delamination or failure, I would say. Do you have anything to say, Erdi, about this?
Yeah, actually, just think about it. If we just put the whole composite direction to the 0. I mean,
Yep.
the whole layers just echoes to the direction 0. So we will be just a really bad buckling shape. Am I right?
Yeah.
So
yeah.
that's why we are using the also symmetrical approach. Actually, we have 8 layers each one. So this is a symmetrical one. Yeah. So the 45 degrees that is actually avoiding the local buckling collapse. Am I right, Bartu?
Yeah,
So
you can say that.
say
You can say that. But in what happens is you're losing your impact absorption a little bit, I would say, because you know
Yes, but
when you put other layers to the impact direction, you're initiating a buckling in fibers for the, because we're using unidirectional fibers in here. So the otherwise your initiation will be on the most of the time on the matrix. Yeah, it will affect a little bit to buckling as well. Sorry, the fiber buckling as well. But I think it's the left side is better at this. And adding a 90 for inner layer is good for stability as well. What do you think, Adi?
also it will be actually much more initial energy occurs if we
Sorry?
say it. That will be much more deformation on the parts. So that's why we can we say that there will be much more initial energy occurs on the right side. I mean the total strain, total elongation of the material because of the deformation.
Yes, but when you think about the combined stiffness, if you you know, yeah, you're right. You're right. Yeah. Okay. Yeah.
So that's all, I guess.
Yeah.
This
That's
is the
all, I guess.
final slide, actually.
Well, it was very
So
interesting. We just had a lot of different topics, and
yes,
I would like to share this recordings with my predictor development team too, because thank you very much, Bartu. You have this work for AI and machine learning part. It was very, very interesting. And thank you guys very much. If you want to add something more, and I will share this recording with the participant, you can contact us anytime you want. And I will share Erdi's and Bartu's contact details as well. And please, anytime you need any information, you can contact us.
last thing that Zaim,
Please.
you can also download the files, the related files of this webinar series from your site.
Yeah.
Am I right?
Yes,
So
we will
sure.
provide it.
Yeah, at the end, I'm waiting for you to give me all this latest up-to-date details, and I will be sharing with all 3 webinar series attendees in once. And well, it was very nice, very good to have you here, guys, and thank you very much again.
yeah.
Thank
Thank
you.
you.
Thank you. Bye.
Bye bye.
Have a good
Bye.
day. Yeah. Bye.
You too. See you.
See ya.
Yeah.